while at the other electrode, the copper ions from the copper sulfate solution take these electrons and deposit as copper metal on the copper plate.
The electrode at which preferential oxidation takes place acts as the anode, and that at which preferential reduction takes place acts as the cathode.
This cell is thus converting chemical energy from the redox reaction Zn solid plus Cu2 plus aqueous gives Zn2 plus aqueous and Cu solid into electrical energy. Such a cell is called a galvanic or voltaic cell. If the concentration of both Zn2 plus and Cu2 plus ions is 1 molar, then the voltage produced is 1.1 volts. Now let us apply an external voltage and see what happens. When the external voltage is in opposition and less than 1.1 volts, the reactions go on as before, that is, zinc going into solution as ions and copper ions from solution depositing on the copper electrode. When external voltage is equal to 1.1 volts, all reactions stop and no current flows. But when the external voltage is greater than 1.1 volts, the reactions now occur in the opposite direction. We have created an electrolytic cell here. An electrolytic cell uses electrical energy to carry out non-spontaneous chemical reaction. This is similar to recharging batteries. When the battery is drained out, direct current is passed through it to reverse the reactions that had occurred during usage. In this way, the battery is recharged. We cannot measure the electrode potential of an individual half cell, as there has to be a reference against which the potential can be measured. So, how do we calculate the electrode potential of a half cell? We do this by measuring the difference between the two half cell potentials. So, if we arbitrarily choose the potential of one electrode, half cell, as 0, then the potential of the other electrode can be measured with respect to this reference electrode. A half cell called standard hydrogen electrode, represented by PtH2H+ aqueous, is assigned a 0 potential at all temperatures corresponding to the reaction as shown. The standard hydrogen electrode consists of a platinum electrode coated with platinum black. This electrode is dipped in an acidic solution and pure hydrogen gas is bubbled through it. The concentration of both the reduced and oxidized forms of hydrogen is maintained at unity. This is done so that the pressure of hydrogen gas is 1 bar and the concentration of hydrogen ion in the solution is 1 molar. So we measure the cell potential at standard temperature and pressure and at unity concentration. This cell potential is the electrode potential of the test electrode, as we have taken the potential of the standard hydrogen electrode as 0. The reduction potential is taken as the electrode potential, and for this, conventionally, we take the standard hydrogen electrode as anode on left side and the test electrode as cathode on right side, as the electron flow occurs from standard hydrogen electrode, the copper test electrode. The measured EMF of the cell with cell reaction H2 plus Cu2 plus gives Cu plus 2H plus. PtH2 bar H plus aqueous 1 molar with Cu2 plus 1 molar Cu solid. That is,
E0 cell is equal to ER minus EL is equal to E0 reduction cathode minus E0 reduction anode is equal to 0.34 volts. E0 cell is equal to ER minus 0 is equal to E0 reduction cathode minus 0 is equal to 0.34 volts. So, ER is equal to E0 reduction cathode is equal to 0.34 volts.
This positive value of the standard electrode potential for the copper electrode indicates that Cu2 plus ions get reduced more easily than H plus ions. Now, the reverse process cannot occur. That is, hydrogen ions cannot oxidize copper under these standard conditions. So now, according to convention, we will have to reverse the electrode positions for zinc hydrogen cell as the electrons flow from zinc electrode to the standard hydrogen electrode. This gives us a negative value for cell potential E0 equals ER minus EL equals minus 0.76 V. The negative value of this standard electrode potential indicates that hydrogen ions get reduced more easily than zinc ions. That is, hydrogen ions can oxidize zinc. Here, our zinc electrode and copper electrodes took part in the reactions, so they are known as active electrodes, while platinum electrode was an inert electrode as it did not take part in the reaction. Inert electrodes like gold, platinum or graphite do not take part in the reaction, but only provide their surface for oxidation or reduction reactions and for the conduction of electrons. So for our Daniell cell, we can calculate the cell potential as EMF of the cell equals E0 cell equals E0R minus E0L equals 0.34 V minus 0.76 V equals 1.10 V. The values of standard electrode potentials for some selected half-cell reduction reactions are given in the table. The arrangement of the electrodes according to their potentials is also known as the electrochemical series. These standard electrode potentials are very important, and a lot of useful information can be extracted from them. If the standard electrode potential of an electrode, as seen from table, is greater than 0, then its reduced form is more stable compared to hydrogen gas. In the same way, if the standard electrode potential is negative, then hydrogen gas is more stable than the reduced form of the species. We can see in the table that the standard electrode potential for fluorine is the highest. This indicates that fluorine gas F2 has the maximum tendency to get reduced to fluoride ions, F-. This means that fluorine gas is the strongest oxidizing agent and fluoride ion is the weakest reducing agent. Also, from table, lithium has the lowest electrode potential, indicating that lithium ion is the weakest oxidizing agent, while lithium metal is the most powerful reducing agent in an aqueous solution. As we go down the table, the standard electrode potential decreases, and with this, the oxidizing power of the species on left decreases, while the reducing power of species on the right increases. We use electrochemical cells extensively for determining the pH of solutions, solubility product, equilibrium constant, and other thermodynamic properties, for determining feasibility of reactions, and for potentiometric titrations.